Hello everyone, and welcome Quantum Coalition representatives to our presentation, where we will answer two questions. One, what are the quantum resources needed to run the quantum approximate optimization algorithm, and how to implement it in Q#. My name is Katie Harrison, and I will be presenting the project on behalf of my teammates, the QCats. This is our team, myself, Mohammed, Nikhil, and Sarah. I'll start this presentation by showing you how we choose our project topic, how we implement it in Q#, our results of running it on Microsoft's Azure Resource Estimator, and finally I'll wrap up with final recommendations as to parameters that you should use when you implement this algorithm on a quantum computer, and possible next steps of how this could be improved. So let's start by talking about project selection. We actually spent the entire first week and a half all reading the papers recommended by the Microsoft Challenge, and each team member chose an additional topic that interested them, read more about it, and presented the following week a project proposal in the form of a 10-minute presentation. During this time, we looked at a lot of things. We looked at QRAM, for example, we looked at sign function algorithms, and of course, we looked at QAOA. In the end, we did decide to go with QAOA as our topic because of three reasons. The first reason is that previous research shows that QAOA is a promising solution to solve a lot of quadratic, unconstrained binary optimization problems. Now, these problems are NP and prime candidates for runtime speedup using near-term quantum computers. The second reason that we chose this as our topic is that while there are actually a lot of resources out there that explore QAOA, we found none that use Microsoft's Resource Estimator to predict the resources needed to actually run QAOA problem on a quantum computer. The third reason that we chose QAOA as our topic was that until 6 weeks ago, this concept was entirely new to all of us, and we decided to use this chance as a learning opportunity. So let's jump into a little bit of what our project was about. QAOA is a hybrid quantum algorithm that is used to solve computational optimized problems. It is based on the adiabatic theorem and is designed to solve QUBO problems. So, as I mentioned before, quadratic unconstrained binary optimization problems. It is important to note that QAOA provides an approximate solution, and I'll explain a little bit about what that means. So, as a high-level overview, QAOA works to provide an approximate solution to problems by preparing a quantum state that encodes all possible solutions, and then evolving that state using p layers of cost and mixer Hamiltonians. Then we optimize those parameters gamma and beta to find the minimum expected value and hence the optimal solution. QAOA can be thought of as the trotterized version of the quantum adiabatic algorithm. So a little bit more of what we mean by that. To run QAOA, we need to go through the following steps. First, we need to express our problem as a quadratic, unconstrained binary optimization problem. This corresponds to mapping our objective as a cost function in the QUBO form, and is usually in the form of a minimization problem. Next, we need to encode the coefficients that we got from the QUBO implementation into a QAOA circuit and run that circuit. Specifically, this is a step that's carried out in Q#. Then, using a classical optimizer, we optimize the parameters gamma and beta such that the expectation value is minimized. Once the optimizer gives us these optimal parameters, we can then put them into the QAOA circuit and get the optimal solution. To talk a little bit about how we tested our implementation of QAOA, we've provided an example. So, we started by exploring the implementation of QAOA by solving the number partition problem with an input list of 1, 5, 6. What this means is that initially you start with a list of 3 numbers, and the idea is you want to split that list into 2 lists such that the difference between the sum of list A and the sum of list B is minimized. So you can see here the sum between list A and B would be minimized if the difference, between these two would be minimized if 1 plus 5 equals 6. So in this case, you can see on the graph that the highest probability in our case is when we correctly partition the input list. So 0, 0, 1 is the best outcome, and in our case, that is when the list is correctly partitioned. Once we encoded and tested our QAOA circuit and classical optimizer, ensuring that they both worked to our satisfaction, we proceeded to apply Microsoft's resource estimator algorithm to our QAOA circuit to determine the number of resources needed to actually compute the quantum circuit and to determine the configuration of parameters that would give us the highest chance of success, while requiring the fewest resources. Our first step was to run and compare the various combinations of qubit types and error correction schemes. At this step, we had a total of 8 jobs, with representing 3 different system setups, including ion qubits, superconducting qubits, and majora qubits. And for each system, we ran one job that computed a realistic and one job that computed the optimistic error rate target. All gate-based jobs were run using the surface code quantum error correction scheme, and the Majorian-based qubits explored both a surface and floret error correction scheme. The graph shown here was made using Azure Quantum's estimate overview function, and all values shown were measured with an error rate budget of 33.3%. The job that stands out most as the best performer is the gate-based ion quantum computer with an optimistic 14.29% T-factory fraction percentage, as well as 252 qubits and a runtime of 216 microseconds. Once we understood these values, to confirm that this was a good option, we moved on to phase 2 of our analysis, examining our error budget. We ran a test comparison for the jobs, comparing the number of physical qubits, the physical runtime, the T-factory fraction percentage, as well as additional parameters, all against a range of error rates. Our results not only confirmed that the gate-based ion quantum computer with the surface code quantum error correction scheme is the best set of parameters to run our algorithm on, it also showed us that we can actually reduce our error budget from 33.3% to just above 9% and still achieve similar output results. However, this improves some things such as our T-factory fraction percentage. So as you can see here, at about 9% is when our T-factory fraction versus error budget really starts to drop off. And what this is showing is that once we hit about a 10% error budget, we start to achieve the same answer. However, we have less T-factory fractions. So what that means is we need fewer T-gates compared to the number of logical and physical qubits to run our system, and we only need to do so at a 10% error rate budget. The similar results are shown as well here. So physical qubits versus error budget, you can see a little bit of a drop off. Once we hit about 9%, the difference in the number of physical qubits needed to run our system is minimal. Finally, I'd like you to see right here, we have a little bit more of a drop off in the physical runtime. Once we reach about 9%, the runtime for our system starts to remain constant, and increasing the error budget would not improve our outcome. In conclusion, we, during this project, successfully developed a working implementation of QAOA using Q# and Python. We ran a comparison of various quantum parameters using Microsoft's resource estimator and offered a database recommendation of which values to use in order to optimize the success of QAOA, and we created a project that can be used for benchmarking different optimization problems that also use QAOA. Possible next steps of how you could improve this. So we recommend, if you have time, and if we had time, the next steps that we would do would be to explore how the resource estimates change when the input list changes length. Would it be linear, exponential? For instance, if our list expanded from 3 numbers to 100 numbers, how would that change our output? The second thing we'd like to look into is why incorrect partitions of our QAOA circuit have varying probabilities. If they are all wrong and they all have equal distance, why are some getting higher error rates than others? The third is we'd like to explore resource estimates when we vary the number of layers in our QAOA circuit. Lastly, we would like to determine a better split of error budget between logical qubits, t-states, and the synthesis of rotation gates, rather than dividing our error rate equally between the three options. Thank you so much for listening. A special thanks to QRISE and Microsoft for supporting this project.